Hi folks, welcome. Today we're going to look at a couple of the practice problems and assessment problems at the end of lesson 1.1.4. It's all about sound and the detection of sound. The Doppler shift equation can be a challenging one to use, so let's do a couple examples, see what we can figure out together here. First, the equation. All right, so this is to say that the frequency detected is equal to the frequency of the source times a ratio. The top of the ratio here is the difference between the speed of sound in a given medium and the speed of the detector, if the detector is moving, over the speed of whatever the wave is in the medium. So if it's sound, we usually use 343 as that value, as a placeholder, minus Vs, which is to say the speed of the source of the sound, the difference between those two values. Let's read question number 2 together. We're in an automobile like the one in figure 7, traveling towards a pole-mounted warning siren. If the siren's frequency is 365 hertz, what frequency do you hear? Use 343 meters per second as the speed of sound. Perfect. If we were given air temperature, we could calculate the exact speed of sound in air as it varies slightly depending on the temperature. We'll learn more about that later on in our heat units when we talk about the particle nature of matter. First, our given values. The frequency of the siren is 365 hertz. Now, one thing that we might have read about earlier is that as we solve problems using the above equation, be sure to define the coordinate system so that the positive direction is from the source to the detector. So that is to say that anything that is traveling from the source towards the detector will have a positive value. Anything that is traveling in the opposite direction will have a negative value. We'll notice in this case, our car is traveling towards the detector, which means it will have a negative value to it. Once again, I'm going to highlight that we have to establish a coordinate system. From the source to the detector is positive. The opposite direction, from the detector towards the source, these are negative values. We're allowed to assume that the pole-mounted siren is not moving. So if it is not moving, we can treat it as 0. The textbook gives you a convoluted set of equations for when one value is stationary and the other value is stationary. I don't know why they're trying to clutter things up and overcomplicate it with a bunch of algebra that doesn't really make it all that much more useful to use. It suffices to say that a fixed object would have a speed of 0. Let's work it through. All right, by subbing in the values, the speed of our detector, our car that's listening to the siren, a negative 25.0 meters per second, so we plug in that value. 343 was the speed in the medium. Our detector is moving 0. 365 hertz times this ratio is equal to, before we calculate, let's cancel our units. In this case, meters per second cancels out. The unit of our final answer will be hertz. 365 times 368 over 343 gives us 392 hertz. Therefore, if you're traveling towards a sound, the frequency should drop, as we see pictured here. All right, again, let's get that Doppler shift question going here for challenge question number 5. Let's list our given values. A trumpet plays middle C. The source, the frequency of our source is equal to 262 hertz. How fast would it have to be moving? Okay, so the speed of the source is our unknown. To raise the pitch to C sharp, so the frequency detected is 277 hertz. This use 343 meters per second. as our speed. We're going to assume here stationary observer. Speed of our detector will be 0. All right, now our unknown is the speed of the source. That's what we're solving for. So let's solve for the speed of the source. All right, again, let's remind ourselves that we're solving for Vs. So that's what we got to get on its own. All right, let's do some algebra. All right, so we've done a little bit of math here. We almost got Vs on its own. Got one more step. All right, let's figure out the speed of our source. So the speed of our source is equal to simplify. 262 divided by 277 times 343 is? All right, so when we sub in all our values after isolating our unknown, we get the speed of our source, 19 meters per second. The trumpet would have to be traveling 19 meters per second for it to be shifted from a middle C to a C sharp. And that's the example for challenge question number 5. Hopefully this gives you a little bit of help. I think the number one issue that students are going to have is likely going to be sign convention. So just make sure that you always establish from the source to the detector as the positive direction. Anything heading in the other direction would be a negative value. All right, thanks.